Hello everyone, my name is Sven Keidel and I work in the software technology group, and today I'm going to give a guest lecture in this course about abstract interpretation. Now, if you have never heard anything about abstract interpretation, it's a systematic approach to implement static analysis. And to start us off, let me take a couple of steps back and motivate why static analyses are important. And for this, we are going to look at a very famous example, in particular at the heartbleed bug. Now, the heartbleed bug was a bug in the OpenSSL library that was discovered in 2014. And this bug affected around 24 to 55% of all the HTTPS websites that were using the OpenSSL library at this time. So this bug really had quite a lot of impact. And so the bug allowed an attacker to read from the memory of web servers. And well, the memory of web servers is very sensitive. There's a lot of different types of information in there, such as secret keys used for the SSL connection, usernames, password, instant messages, emails, and so on. And essentially, this was a very serious vulnerability here. So how does that bug work? Essentially, this bug was part of the heartbeat protocol. So essentially, a client sends a message to a server to trying to figure out if the server is still up or and responding. So essentially, the client sent a heartbeat message which contains some payload which the server is supposed to send back just to figure out that the server is still alive. And then this heartbeat message also contained the length of the payload here. However, the client, if it was a malicious hacker, for example, could have just returned a wrong payload length here, such as 500, which is clearly longer than the real length of the payload here. And then the server would return the payload, but also everything else that comes past the payload inside of the memory of the server, such as passwords and so on. And essentially this allowed the attacker to read from servers even without having direct access to the server. So clearly this bug was a very serious vulnerability, and it caused a lot of damage because it allowed hackers to get into servers. So, but how could such a bug be prevented? Well, let's look at a couple of techniques that would allow us to prevent such a bug. And here I want to essentially compare and contrast a couple of these techniques along two dimensions. Here on the x-axis, I want to compare the effort and the expertise that is required for each of these techniques. And here on the y-axis, I want to compare what kind of correctness guarantees do we get from these techniques. And I mean, one of the most well-known techniques is, of course, testing. So in testing, essentially the programmer writes down a number of unit tests or integration tests to assert that a program has a certain behavior. For example, here we want to test that the function foo never returns null. And well, testing requires a certain amount of effort. Essentially, you need to create these tests. You need to maintain these tests whenever something changes. But also it requires a certain amount of expertise. It requires domain knowledge. For example, The programmers of the OpenSSL library certainly would need to know the details of the SSL protocol to write tests for it. However, the problem is that with this technique is that it only gives us a low amount of correctness guarantees. Essentially, the OpenSSL library was very well tested, but still the tests missed this critical vulnerability. And so testing only allows to show the existence of bugs, but it cannot prove the absence of bugs, which is a famous saying from Edgar Dijkstra. So what other kinds of techniques are there? Well, there's, for example, formal verification. And in formal verification, a programmer performs a formal mathematical proof that some property about the program holds. For example, here we show that for all inputs n, the function foo never returns null. Now, this technique requires a lot of expertise because essentially the programmer has to perform a mathematical proof that this property holds. The programmer has to know about mathematics, the programmer still has to know about the domain knowledge of the program. And this costs also a lot of effort to perform these mathematical proofs. This is not as easy as just writing down tests. You have to think about what the program is doing and how you can show these properties. However, formal verification also provides a high amount of correctness guarantees. In particular, if you can show such a proof, then the property holds. Now you may say, well, the proof itself may have mistakes in it. Well, that's true, but these days there are very good software tools that allow you to check that the proof itself is correct, which gives you absolute 100% guarantees that this property is very satisfied. But of course, there's another technique we want to look at, which takes less effort than formal verification, which is the technique of static analysis. Now, static analysis is a software tool that verifies a certain program property. And essentially the software tool is completely automatic. It looks at the program code and tells you, well, this program property is satisfied or is maybe not satisfied. For example, here this analysis may say, well, the function foo does never return null. And because this is an automated software tool, it only requires very little effort. Essentially, the programmer only needs to run the tool. And it also requires very little domain knowledge because and expertise because, well, it's a software tool that works automatically. But also these static analyses, if they are designed correctly, they provide a high amount of correctness guarantees. Essentially, if the analysis itself is correct, then the guarantees that it provides are also correct. And we are going to look further in what this correctness for static analysis means later on in the lecture. So what exactly are static analyses? As I said before, static analyses are automated software tools that look at the source code of an application and extract some information from the code. But in particular, these static analyses, they do not run and execute the code. But they extract the information without running the programs. And this differentiates static analyses from dynamic analyses. Dynamic analyses, on the other hand, they produce and extract this information while they run the code. Now, static analyses have a wide variety of different use cases. For example, static analyses can be used to find bugs in applications. For example, they can find type errors, they can find null pointer exceptions, or if an array has been accessed out of bounds. They can also be used to analyze the security of an application and find security leaks, such as memory leaks, like with the OpenSSL bug that we saw before. They, for example, can also detect SQL injection attacks with taint analysis, for example. And lastly, they are also used very extensively in compiler optimizations. For example, moving code out of loops to speed them up, or to remove dead codes, and so on. And essentially today we are looking at a specific technique to design static analysis such that the analyses are sound. And this technique is called abstract interpretation. And in the second part of this lecture, I'm going into more detail about abstract interpretation. So in the second part of the lecture, I want to demonstrate the concept of abstract interpretation by designing static analysis for a very simple language. So we will start by defining the semantics of the language itself, because, well, we are analyzing this language, so we have to know what the semantics of the language itself is. And in particular, we will write down the semantics in a big step style. So let's look at the language first. So here I just want to look at a small language which has expressions. And the expressions can be either number literals, or they can be additions, for example. Or there could be other expressions as well. Now let's write down a big step semantics for this language, which I think you should already know about what this type of semantics is, but nonetheless. So essentially we write down rules which tell you how the expressions of the language evaluate to a value. And we have one rule for numbers, which basically say if we have a number n, then this evaluates to the value which is just the number n. For addition, the big step rule would look like this. We have an addition of two sub-expressions e1 and e2. Now we want to evaluate that. For this we have to first evaluate e1 to a value, v1, and we have to evaluate e2 to a value, v2. And then we can check that both v1 and v2 are numbers, and then we just have to add these numbers together. v1 plus v2. Now, the benefit of such a big step semantics is that we can implement the semantics with an interpreter in a meta language of our choice. And in particular here I want to implement an interpreter for this language in Haskell. And this is going to be a big step interpreter. This interpreter takes as input, it's a function which takes as input the expressions of the language, and maybe something else like an environment, and it returns the value, a value for evaluating this expression. And this value for our language may just be integers, for example. Now, how does how do we implement such an interpreter itself? That's just the type signature. Well, we have to first of all pattern match on the expression E with this case construct of Haskell here. And then we have two cases. We have either the number case, in which case we simply return n, or we have the addition case of E1 and E2. And here we do the same thing as in the big step rule above. We simply evaluate E1 and E2. And then we just add both of the values together. Now, so this is essentially a very simple programming language, and we have written down two different ways of specifying the semantics of the language. We have written down the big step semantics, and we have written down a big step interpreter which interpret the same language. And so essentially we can do the same thing when analyzing the language. In particular, we can write down a big step abstract interpreter which essentially evaluates the same expressions, but it does not return a number, it returns an analysis result. And we are going to see how this works in a second. But before we get to designing an abstract interpreter, we have to figure out what program property we want to analyze, because there could be many different properties we want to analyze. So we have to decide on one and then design an abstract interpreter just for this particular program property. So how does that work? So these program properties, they can be described with a particular type of semantics, which is called a collecting semantics. And this collecting semantics is described over the semantics of our language that we have just defined before. And these collecting semantics then allow us to specify the properties that we want to analyze. For example, we could write down a program property in form of a collecting semantics that says that a function in a program can never return null. And we would do this by saying the following. We could say we have a set such that when we evaluate a program foo, for example, and we have an environment env where the environment is just any possible environment, then this set is not allowed to contain the value null. Right, so essentially this set here is called the collecting semantics, and this collecting semantics says something about all possible evaluation of the program foo, and in particular we want to vary the inputs of the program which are specified with the program environment, and then we can specify the property that there can be no null pointer exception by saying that this set cannot contain the value null. So a case in which the interpreter evaluated the program under a specific environment to the value null. But we can also find other interesting properties that we want to analyze. So let's look at a few more examples here. For example, we could be interested in that the output of a program is constant, which means that no matter how we change the environment, we will only get the same result back, only just one result back. Well, we can also do this with the same collecting semantics. In particular, we can say that if this set here is a singleton set containing only a constant c, then essentially the program foo is constant itself. Let's look at another example. We could, for example, be interested in that a program can never fail due to an array access which is out of bounds. Well, then again, we can use the same collecting semantics. And then say that this cannot have an array out of bounds exception. So essentially these collecting semantics allow us to describe program properties that we want to analyze. Okay, so before we have described the collecting semantics that allows us to ask questions about programs that we want to analyze. But the collecting semantics is undecidable, which means that there is no computer program that can precisely calculate it. So instead, what we can do is we can approximate the collecting semantics with an abstraction. And today I want to talk about a very simple abstraction as an example. In particular, the sign abstraction, which allows you to find out if a program evaluates to a positive number, a negative number, or zero. And we define the sign abstraction by defining a so-called abstract domain. And this abstract domain is a data type sign, which is either pos or zero or neg. So these three values stand for the infinite sets of positive numbers, 1, 2, 3, and so on. The set which contains exactly 0, and the negative numbers. -1, -2, and so on. But also the analysis can be unsure if a program evaluates always to nec or 0. Therefore, we need some other values which represent these cases. In particular, we need a so-called top value, which stands for the set of all numbers, including positive, negative, and 0 numbers. So -1, 0, +1. And we need an extra element which stands for the empty set, bottom. And so this relationship now defines some kind of ordering between the elements of the abstract domain. In particular, this ordering is as follows. We have the least element, which is the bottom value. Then we have pos, 0, and neg, which are greater than the bottom value. Therefore, I draw them above above the bottom value. And then there's the top element, which is greater than all of the other elements. Therefore, I draw it on the top of this diagram. And this diagram is called a Hasse diagram. And it defines the ordering of this abstract data type. And this ordering tells us which of the abstract values are more precise than other values. Now, this relationship of how the values of the abstract domain relate to the values, the sets of values, this relationship is called a Galois connection. And the Galois connection consists of two functions going in one and the other direction. So one of these functions is called the concretization function, and it goes from the set of abstract values to the set of concrete values. So it takes a sign as input and it produces something in the power set of values. And so this is exactly the mapping which I've written up here. This up here is gamma. But there's another function which goes in the other direction, which is called alpha. It's the abstraction function, which takes a set of values as input and it returns an abstract value as output. And in particular, this abstraction function returns the abstract value that most closely approximates the set. For example, we have the set -5, 3, -3 and -1. And the abstract value that most closely approximates the set is the negative value. But also we could have another set like this, for example, -3, 0 and 1, for example. And here we have negative values in here. We have 0 in here. And we have positive values in here. So the value that most closely approximates these three cases is the top value. because when you look at the corresponding set of the top value, it's the set of all numbers. And so the set -3, 0, and 1 is contained in the set of all numbers, but it is not contained in the set of positive numbers in the set 0 or in the set of negative numbers. Therefore, top is the only value that contains all of these numbers. And so what this function does is it computes the least upper bound of all of these values. And the least upper bound is essentially an operator which is defined by the ordering of these values. And you can read this in the Hasse diagram, what the least upper bound of two values is. For example, the least upper bound, and let me write this operator down, of 0 and neg is the top value. And you can see this by looking at the diagram. You have 0 here, you have neg here, and the smallest value that is an upper bound of 0 and neg, so that is greater than 0 and neg, is the top value. Therefore, top is the least upper bound of 0 and neg. And this is how you compute essentially the value of the abstraction function by taking the least upper bound of all of the components of the set. So let me go into a little bit more detail about what it means that alpha and gamma are a Galois connection. And we can draw this as a diagram here where the set of values, power set of values, is a Hasse diagram here on the left-hand side, and sine is another Hasse diagram on the right-hand side. Now, for alpha and gamma to form a Galois connection, we need that if we take any set of values in here and we map it to some sine value over here with the abstraction function alpha, and then we map it back using the concretization function gamma, we end up somewhere at a point which is greater than where we started off. In particular, this here has to be smaller than. And the other way also holds. So if we go from the other way around, if we start from an abstract value here and we go over here with the concretization function, and then we take the abstraction function back, we end up at a point which is smaller than the value before. And I use this ordering symbol here for smaller than on the abstract values. Now, when you write this down, not with a diagram, but with formulas, this looks like this. So we have for all x element p-val, x is a subset of gamma alpha x, and conversely for all y sine we have alpha gamma of x of y, sorry, is smaller than y. So if the two functions, the abstraction function alpha and the concretization function gamma, satisfy these two properties, then they form a Galois connection. There's a special case of a Galois connection which occurs quite frequently, and in particular for the sign domain that we've seen before, this is the case, which is that here in the second equation we don't have a smaller than, but we have in fact an equal. So when we take the abstraction function and then first the concretization function gamma and then the abstraction function, we end up at the exact same point as before. And in this case, this is not called a Galois connection, but it's a Galois embedding. And in fact, most of the cases that we are working with are actually Galois embeddings instead of proper Galois connections. Okay, so next we want to design a sign analysis for the programming language that I showed in the beginning. And the interesting thing is that we can make use of this Galois connection, which I've defined before, to derive the sign analysis, which means that there's a very systematic way of defining the analysis without having to choose and perhaps make a mistake. And here in this, to start off, I want to look at a very simple example, namely, let's say we want to define the semantics of the addition operator, the sign semantics. So we have addition here, and let's say we get two abstract values, namely 0 and pos. And we want to figure out what the analysis result of this addition should be. Now, everyone that thinks a little bit about it will find out, well, if you add 0 to a positive number, the result should of course be a positive number. But we can use the Galois connection to derive this systematically, which will help us in cases where the semantics, the static semantics, is not as obvious as here in this example. So in particular, we will use the, first of all, the concretization function and apply it on each operand of this addition. So here, if we apply gamma on 0, we get the set 0. And then if we apply gamma on pos, we get the set of all positive numbers. Now we apply the concrete addition operator on the Cartesian product of both of these sets. And so what we get is a set in which we add 0 of the left set with 1 of the number of the right set. So we have 0 plus 1, 0 plus 2, and so on. And when we evaluate that, we get that this is the same as 1, 2, 3, and so on. And now we take the abstraction function to give us an abstract value, a sign value for this. And so the sign value that most closely approximates the set is the value pos. And this is how we define the abstract version of plus. And since this is confusing, since now we have always an abstract version of plus and a concrete version of plus, I will use these hat symbols on top of the abstract versions that we don't get confused with concrete and abstract things. Now let's do another example. Let's look at something which is perhaps maybe not that obvious. Let's look at adding pos to neg. And let's do the same procedure again. So let's take the concretization function here and here. So we get the set of positive numbers and the set of negative numbers. And then we add them together. So what we, for example, get is if we add 1 plus minus 1, we get 1 minus 4, for example. We get 2 plus minus 1, and so on. So essentially, when we evaluate that, we get 0, minus 3, plus 1, and all other numbers. So if we take the abstraction of that, the abstract value that most closely represents the set is the value top, because the set contains positive numbers, 0, and other numbers as well. And so top is the best possible approximation. And this is how we define the abstract semantics in this case for plus. And we can do this for essentially all the cases of pos, neg, and 0, and define a table which shows how the two operands map to an abstract result. This table looks like this. So we have here the one operand, neg, 0, pos, and top, and we have the other operand, which is neg, 0, pos, and top. Then we can just fill this out, and we get neg, negative, and 0 is negative. And the example below shows that negative plus positive is top, and something plus top is also top. So here in this column we can fill out all the top values here as well. Now let's do the second row. We have 0 plus something is always the other thing. So we have 0 plus neg is neg, 0 plus 0 is 0, 0 plus positive is positive. And now we only have the last row, which is 0, pos plus neg is top, pos plus 0 is pos, and pos plus pos is pos. And essentially this table then defines the abstract semantics for all of the cases of the abstract addition operator. So to better understand this concept of abstraction, let us look at another abstract domain. And in particular, we will look at the Boolean abstract domain. And the Boolean abstract domain is very simple. You have a bottom value, you have a top value, and then you have true and false. And so true and false are incomparable, therefore they don't have lines drawn between them, and top is greater than true or false, therefore it's above them and has two lines attached to true and false. Now let's look again at the Galois connection for this abstract domain. And you should be able to do this yourself right now, so feel free to pause the video and do this yourself. But so we have a concretization function which goes from the abstract booleans, and I will use a hat symbol to distinguish it from the concrete booleans. And it goes to the power set of Boolean values. And so this concretization function is defined as mapping, I should probably use hats here as well. This maps true to the set with just true in here. It maps false to the set false. And it maps top to the set which contains true and false. So this represents a case where the analysis is uncertain if the result is true or false. And then finally bottom is mapped to the empty set. By the way, this bottom value here, this is used for non-terminating programs. So whenever the program that you're analyzing does not terminate, you return the bottom value of the abstract domain. And so the abstraction function, on the other hand, works as the working is quite obvious. Like when we have, for example, the set true and false, the abstract value that most closely corresponds to the set is the value top. Now let's look at an example of an operator for this Boolean abstract domain. And in particular, I want to look at the AND operator, the conjunction operator. And for example, let's say we have the abstract value false, and we want to take the conjunction of false with a Boolean value which could be either true or false. Now again, we use our technique for deriving the abstract domain instead of thinking hard about it. And so we apply the concretization function to both of the arguments. So this will give us the set false. And applying the concretization function here gives us the set true and false. And now we map this with the concrete conjunction operator, and we get false and true and false and false. So when we evaluate that, we get false for the first case, because false and true is false, and false for the second case, because false and false is false. And now we take again the abstraction function, which gives us the abstract value which most closely represents this result, and this is in this case false. And this is where how we define the abstract conjunction operator for this case. Now the interesting thing to note here is that even though one of the arguments of the conjunction operator is top, so the most imprecise value that we could think of in the Boolean domain, the abstract semantic still doesn't return top, it returns false, because in all of these cases because one of the arguments of the conjunction is false. No matter with true or false with which we take the conjunction here, the result is always going to be false. So even if one of the arguments of the operator is top, then the result doesn't necessarily need to be top. Now let's use what we have learned so far and apply it to implement a static analysis. And in particular, we will implement the sign and Boolean analysis as a big step abstract interpreter. Now, this big step abstract interpreter is essentially an interpreter which interprets the expressions of the language that we want to analyze. But instead of returning a concrete value like a number or a Boolean, for example, the abstract interpreter returns an approximation of the analysis of the program. And so we can implement such an interpreter in a meta language such as Haskell with a function eval het, which takes an expression, so the expression we want to analyze, and an approximation of the inputs of this expression, so an abstract environment, and it returns a value, but an abstract value, which represents the analysis result for this expression. And this abstract value can be, for example, a sign value, it can be an abstract Boolean, or whatever other values you have in your language. Now, this abstract interpreter essentially does the same thing as the concrete interpreter. It takes the expression and it performs a case distinction on this expression. And in case we have, for example, a number literal, we now have to return a sign value which most closely represents this number. And so we can do this with, for example, an if statement. If n is smaller than 0, then return the abstract sign value 0. If n is equal to 0, then I messed up. There should be neg, of course. This should be 0. And in all other cases, return pos. Let's do one more case here. For addition, E1 and E2. And here again we do the exact same thing as in the concrete case. In particular, we evaluate both of the sub-expression to an abstract value. So we have eval het E1 inf, and we have V2 eval het E2 env. And now we return the result of adding V1 to V2, but we use the abstract version of the addition operator that we have defined before. And we essentially do the same thing for all other expressions of the language. And in the lecture notes, you can find a more extensive version of this interpreter for some other language constructs as well. Okay, so let's take a step back. In the beginning, we have defined a big step interpreter, which defines the semantics of the language. And later on, we have defined an abstract interpreter, which implements an analysis for this language. But now we want to know if the results that the abstract interpreter produces somehow faithfully reflect the behavior of the language, so that the abstract interpreter just doesn't do something completely wrong. And this is specified by a property which is called soundness. And static analyses, it is very desirable for them to be sound. Specifically, if you use these types of analyses in, for example, compiler optimizations, then it's very important that the analyses that you use are sound. Otherwise, the compiler might optimize a program and accidentally change the semantics of the program, which really leads to very unexpected behavior. So for static analyses that are used in compiler optimizations, they have to be sound. There is no way around it. Now we can write this soundness down as a mathematical property which relates the collecting semantics of the concrete interpreter to the abstract semantics of the abstract interpreter. So in particular, for all expressions E, and all abstract environments the abstract interpreter should over-approximate the concrete collecting semantics. So when we call the abstract interpreter eval on E and env hat, then this should be an over-approximation, so it should be greater than the abstracted concrete collecting semantics. So eval of E env, where env is an element of the concretization of env hat. So the interesting thing is that this is essentially the same property than what we did when we drew these diagrams from before to derive the semantics of the abstract operations. So in particular, we start here from an abstract environment env, and we can apply the abstract interpreter eval to the program E and the expression env hat. And then we end up with some abstract value. And this has to be greater than going the way around here, taking the concretization function, which gives us a set of concrete environments, to which we then apply the concrete interpreter eval. To get a set of concrete values, and then taking the abstraction function. So as you can see, this diagram has a very close correspondence to the diagram that we wrote before. And in particular, when we wrote these diagrams to define the abstract interpreter, the abstract operations like plus with a hat on top, then we did nothing else than doing a soundness proof. In particular, we have used the soundness proof to guide us to derive the static analysis. And this is the power of this approach. The soundness proof guides us in how we should define the static analysis. So there's almost no choice in how we should define it. We can just derive it using the soundness proposition and doing the soundness proof. So let me summarize. So in this lecture, I've shown you why static analysis is important. In particular, static analyses are automated tools that analyze the source code of your program without running it. And I've shown you a specific technique called abstract interpretation, which allows you to derive a static analysis by following a formal soundness proof. And so in the homework, I invite you to do a couple of exercises to derive more abstract operations and define your own abstract interpreter. Thank you very much for the attention.